So in 1800s, a guy named Laplace was playing with some integral operators, and he discovered that exponential integrals tend to have numerous applications in so many different fields, in differential equations, probability theory, complex analysis, and so on. Matter of fact, I was recently carrying out some research in number theory, and I discovered a fascinating application and use of the Laplace transform in number theory. But I'm gonna keep that to a later video, or probably keep it a secret to myself. Um, Even nowadays, people in coding theory and signal processing, they tend to use the Laplace transform for so many different purposes. So the purpose of this video is to introduce the Laplace transform and some of its basic and general properties, just in case somebody's living in the dark and doesn't know about it. Or maybe just in case you want to refresh your mind, that's going to be a good place to do that. This is our guy, this is Laplace, by the way. So I will have to begin by defining what that is, but let me mention that typically people in differential equations love Laplace transform because it kind of take complicated calculus and map it to simple algebra. And the reason is Laplace transform maps derivatives in the time domain into polynomial variable into polynomials in the S domain. And we're gonna discuss maybe this application briefly at the end of the video, but for now let us go ahead and define what that thing is. So Laplace transform is also an integral operator defined in this way. You take your function of interest and you hit it by an exponential kernel, and you integrate from 0 to infinity. So this takes a function from 0 infinity, let's say c, let's call it a nice function, and maps it to a function that we're going to denote by LF, and that's going to be defined on some right half plane. So this is going to be defined, so we have the complex plane, and this is going to be defined for some right on some right half plane. But let me point out an interesting thing about the Laplace transform, which is that it's basically the Fourier transform of some modified function. So usually we use the Fourier transform to analyze frequencies of a signal, for instance, and it's pretty fascinating to observe or to realize the Laplace transform as a Fourier transform of some modified function, and that's because if you write the S variable as sigma plus I omega, then you can observe that these two integrals are one and the same if you were to expand the S as sigma plus I omega t. So if you just kind of do this basic operation, you can recognize the Laplace transform as a Fourier transform. However, the purpose of this video is to focus on the Laplace transform, so I guess let's go and do just that. So more formally, this is how we define the Laplace transform. We define it whenever this improper integral converges. However, when does it converge? Well, we need f to be nice enough in the sense that we need it to have at most an exponential growth of some order. So if we assume that f is of exponential order alpha, in other words, it could be bounded by an exponential function in this way, where alpha is going to be called the order or the exponential order, then the Laplace transform is going to be defined on the right half plane. So this is going to be alpha, and on the right half plane, the Laplace transform is going to be defined, and matter of fact, it's going to be holomorphic. In other words, this integral that we defined over here, it's going to exist first of all, and then it's going to be also a holomorphic function of S. So this requires a proof. However, this is an elementary fact, so we don't want to spend a lot of time justifying that. But here's a quick way to justify it, I guess. So we're dealing with the Laplace transform, which is so let's write it again. So the Laplace transform of f as a function of s, it's defined as the integral from 0 to infinity of the function e to the minus st f of t dt. And given the fact that we know about f, given the niceness of f, let's say, we can bound this as the integral of e to the minus sigma t times, let's say, e to the alpha t dt with some constant m over here. And then this thing basically is the value m over sigma minus alpha, which is finite. And I'm gonna leave it to you as an exercise to figure out where we've used the fact that sigma is bigger than alpha, but that's not a hard thing to justify. And given that this integral converges by something like the comparison test from calculus. Okay, so now we know that as long as the real part sigma of s is bigger than alpha, the Laplace transform of any function of exponential order alpha is going to exist on the right half plane real of s bigger than alpha. Okay, so this is a basic fact about the Laplace transform. So this is just the minimal thing we need to be able to deal with this thing and make sure we're not dealing with something nonsense. So as I mentioned, more is true. We can even prove that this integral or this function, this new function we're denoting by LF, it's actually analytic, it's holomorphic. In other words, it's complex differentiable on that right half plane. And this requires a proof, so maybe we can also give a quick proof of this. But this is also elementary, so we won't spend a lot of time. But the fact that we're able to prove something like this is very interesting because when we're dealing with holomorphic functions, things are way, way nicer. So maybe I'm gonna go ahead and prove that for you. So if I'm gonna call the Laplace transform LF, I'm gonna call it by, I'm gonna give it the name f of s just for simplicity. And remember, we're proving that this function is holomorphic, it's complex differentiable on this right half plane. Okay, so here's a quick way to see that. So we want to prove that the limit defining the derivative exists. Of course, if we look at, let's say we fix a point s naught in the right half plane h alpha, and we look at f of s naught plus h minus f of s naught over h, this could be rewritten by linearity of the integral as the integral from 0 to infinity of e to the minus s naught plus h times t minus e to the minus s naught t divided by h times f of t dt. And from there you can see what we're heading to. We're gonna interchange the limit and the integral after we pass h to 0, and we're allowed to do that because f has exponential order. So in other words, if you look closely here, you see that this thingy it's gonna converge to the function minus t e to the minus s naught t as as h goes to 0. Basically, that's the derivative of the exponential function. And we're interested in the limit of this thing, but the limit of that is gonna thus be just the limit of just the integral of the limit that we have. So as h goes to 0, this is just the integral from 0 to infinity of this thing, f of t dt. In other words, I'm able to pass the limit, interchange the limit and the integral. Just to be a little bit more careful, let me quickly justify to you why this is the case, why we can do that. So maybe let me call the integrand g of t, let's say, and keeping in mind it depends on h. Well, it's easy to observe that g of t, for instance, you can do some bound like that. You could use the triangle inequality and the fact that the real of S naught plus h is bigger than alpha, given that h is small enough, and you can thus obtain a bound like, you can bound g of t by something like some constant times t, let's say times e to the minus sigma naught plus, minus alpha times t. So something like that, you can obtain a bound like that. And that's pretty easy to do just by the triangle inequality. And then from this bound, you can observe that you dominated this function, which depends on h, by the way, by a function that doesn't depend on h. And it's also integrable in this because sigma naught is bigger than alpha, and interchanging the limit and the integral is thus allowed or justified by something like the dominated convergence theorem. I'm gonna let you look that up, or you can justify it by the absolute convergence of the integral or whatever you wanna do. So bottom line, now we have this function LF that takes a function f that is defined on 0 infinity and nice enough in the sense that it's of exponential order alpha. And what it does is that it gives us a function that is complex, first of all defined on the on some right half plane, and it's holomorphic. It's not only defined there, it's holomorphic there. And that's a very important property that we're gonna see how to use it later on. Now, the next thing we want to do is that, so since we're speaking of this operator, it better be unique in some sense, right? So we don't want to like, when we take the Laplace transform of some function, we're interested in some decay or growth properties that we like to study. And it's thus justified to kind of hope that this operator is kind of a unique mapping in the sense that, so if you look at this, again, if you look at this Laplace transform, if I give it two functions, LF, so I give it F1 and F2, and these two are equal in some sense, then we better hope that F1 is F2. So it's natural to hope for something like this. And this is true, let's say almost everywhere, let's put it this way, with things to be defined. And this is indeed true because of this realization that you can make. If you realize the Laplace transform as a Fourier transform, this uniqueness fact is almost immediate. But we're gonna present that and prove that anyways quickly. So a fact like this is gonna be important for reasons to be discussed later. But this is the fact that if you have two functions of let's say of the same exponential order, and their Laplace transforms are equal, then necessarily the two functions are equal, let's say almost everywhere. And let's keep this vague, but you can think about it as almost everywhere, but it's a measure theoretic thing that I'm not, that's not the purpose of this video, but it could be defined precisely, let's put it this way. So if you introduce the function f1 minus f2, what you know is that if you introduce a function g of t, that is some modified version of this function, let's call it e to the minus sigma t f of t, then what you have is that you have that the Fourier transform of that function is precisely the Laplace transform of f at sigma minus I omega, or excuse me, plus I omega. So this fact we know from the observation we made over here. If you take the Fourier transform of this, it's going to be the Laplace transform of the original function. And we already know that the Laplace transform is 0. So we already know that the Laplace transform is 0 of f because of linearity of the operator L, right? So L is just the integral of some kernel times f1, and same for f2. So if you subtract these two, you get that the Laplace transform of f1 minus f2 is necessarily 0. And hence we got that the Fourier transform of this function g is 0 for every omega in R. But this is enough to get that g is 0 almost everywhere. Okay, this implies g is 0 by Fourier analysis. This function is 0, let's say, almost everywhere, which in turns imply that f is 0 almost everywhere because you can divide by this thing, and we have the fact that we claimed. So the uniqueness is almost immediate from facts we know from Fourier analysis, and so this is the first place where the importance of this realization of the Laplace transform as a Fourier transform pops up, and it's pretty fascinating. Like, you can use tools from other theory to do stuff in your theory, which is very good. But from now on, if you have two functions and they have the same Laplace transform, then they're almost the same. Let's put it this way. Next I want to talk about how the Laplace transform act on basic or special functions like these. So given that you can kind of represent any function as a power series, or let's say any nice function as a power series, let's say analytic function as a power series, it's enough to study what happens to the Laplace transforms at power of t to be able to study what happens to the original function. Even in cases where you can't represent the function as a power series, and you can still kind of find an asymptotic series of it, this will be enough. It will be enough to know an asymptotic series of the function, to know an asymptotic series of its Laplace transform under some not so bad conditions. In other words, knowing how the Laplace transform maps these simple functions is going to be enough for us to know how it maps some other complicated functions. So it's fascinating, and these identities, these equalities, are just basic calculus. So you can obtain them by just a matter of maybe integration by parts. But for example, this is immediate, this one maybe you need some integration by parts, and this one you get it by induction. So it's important to remember these functions. And by the way, for example, why is this defined on the real of s bigger than 0? Well, it's because we're taking the Laplace transform of 1, and 1 is of exponential order 0 because it's less than e to the 0, right? So the alpha here is 0. So these are some interesting things to observe. For example, this one is of exponential order a because e to the at is like trivially bounded by an exponential order alpha equals a. So these things are interesting to observe. As I mentioned, if you know how these get mapped, then you know how any function get mapped. Stuff we're gonna probably discuss later. One important thing, or maybe if you don't wanna remember these stuff, one important thing to remember, and that's pretty important, is that polynomials, so you can summarize all of these above by remembering something like polynomials in T get mapped to let's say, polynomials in 1 over s. And that's an interesting property on its own. So next, we're gonna quickly discuss some basic properties before we talk about the applications. So first of all, we have linearity, and that's trivial because the Laplace transform is an integral, and the integral is a linear operator. And then we have the scaling property, which is that if you scale the input to the function that you're applying the Laplace transform to, and you look, for example, if you look at the definition of the Laplace transform on the left, you're going to have something like e to the minus st times f of ct, but we can always introduce a change of variable to get what we wanted, to get this property. So you can introduce a change of variable like u equals to ct, and then carry out the integration, the change of variable thing, and you see that you arrive at something like this. And another property that is of particular importance because it shows up a lot is the exponential shift property of the Laplace transform. In other words, if you want to compare the Laplace transform of your original function and a shifted version of it, this is how they relate. But that's a trivial thing to observe, because if I have a function f of t, and I'm taking a Laplace transform of it, so this is what it is. But if I hit it by some exponential term like e to the at, this is the same thing as, I don't know, e to the minus s minus a t f of t. But if you look closely, you observe that this thing, the above thing is the left-hand side, and the below thing is the right-hand side, because you're evaluating at s minus a instead of s, and that's the same thing. So these properties are very important to remember. So some other things I wanted to discuss with you are the inverse Laplace transform, how to invert this thing. In other words, if you take a Laplace transform of some function, or if you know the Laplace transform of some function, can we map back? And the answer is yes, we can. But it's going to be some contour integral instead of a real integral. So and matter of fact, this thing is the way you can derive all of these Laplace tables that you see, Laplace transform tables that you see, that connects the Laplace transform and its inverse, because if you're a bit familiar with complex analysis, you can shift this contour that is, so this contour, what it is, it's there's some sigma here, and we're integrating from minus I infinity to plus I infinity over this line, and we can shift this line, and we can pick up residues as we shift the line. And if you're not familiar with complex analysis, this is a bit hard to follow, but I wanted to mention that if you know how to invert the Laplace transform, and if you're a bit familiar with complex analysis, then deriving the tables for the Laplace transform that is relating the Laplace transform and the inverse Laplace transform is a piece of cake. It's a matter of computing residues of functions, but let's keep that to a later video probably. Maybe some final things before we go to applications. Let's quickly discuss how the Laplace transform deal with derivatives of functions. Well, this is not so hard. It's just a matter of observing that if I pass the derivative of some function into a Laplace transform, then it's really a matter of an integration by parts to observe that this thing is exactly as this thing, because you could integrate this by parts. I don't know, something like e to the minus st f of t between 0 and infinity minus the integral of the derivative of this times f of t dt, and this thing is going to be a Laplace transform with some s carried out, and so there's a derivative here, and this thing is going to be f of 0. So if you assume that f is of exponential order, then the value of this at infinity, the value of this at infinity is going to disappear, and you end up with just f of 0, because this thing at 0 is 1. So such things are important to sit down and do them by hand, but all I want you to, the message behind this video is that these basic properties can really be derived using some basic calculus, integration by parts, whatever, you name it. And of course, you can generalize such an identity to an nth derivative identity by induction, right? So you can prove something like this by induction on n. So maybe for now, let's postpone these little details to a later video and discuss a bit the applications just quickly before we wrap up this video. So, you know, sometimes we people in different people that do PDEs or ODEs, they're interested in solving equations like this, differential equations like this. So the Laplace transform here comes at our disposal to turn complicated calculus into simple algebra. In other words, turn derivatives into some polynomials and some powers of s. And that's all we need to solve such an equation. So if I take this equation and I apply the Laplace transform on both sides, I can use linearity to arrive at something like this, because the Laplace transform is linear. And then I can use the fact that the Laplace transform maps the derivative in this way. And once I know that, I've turned this equation that has derivatives in it to just an algebraic equation like this, which could be solved easily by kind of rearranging stuff, and you can solve for the Laplace transform like this. And after you've solved this, after you arrive at this, you have this thing, and you can go to your favorite Laplace table, Laplace transform table that relates the Laplace transform and its inverse. And if you know the Laplace transform of a function and you want to get the inverse Laplace transform, you can get it from a table or whatever. You can like shift the contour and calculate the residues, just as we mentioned, using the inverse Laplace transform formula. So it's really a fascinating tool. It's really a very powerful tool, and you really have to do things by hand to appreciate how powerful it can be. But like using Laplace transform is really a matter of just bookkeeping and then mapping the Laplace transform back to the original function. In other words, if we like apply Laplace inverse here, we get the y that we're looking for. And remember, here we were solving for the y here. Of course, this process could be generalized to higher order differential equations, and you can still apply something like this to solve higher order differential equations. For instance, you can solve a second order ODE like that in a similar way. And most of the time, especially if you know the Laplace transform of the function here, and with some other assumptions, you can kind of invert things back to the original function. In other words, you can use this process to solve higher order ODEs in a similar way. Okay? And it's as an exercise, it's interesting, for example, to pick a special function f, a special number here a, and a special number here y naught, and I don't know, look up the solution of the differential equation, and then solve it using the Laplace transform and see if you get the same thing. So that's a pretty interesting thing to remember. And then, as a final thing, let me discuss quickly some probabilistic application. So, you know, Laplace himself, he was a probability theory guy, or at least he was interested in probability theory. So it's kind of a shame not to relate these to probability theory as a final thing in this video. So if you have a random variable x and you have its density f sub x, density function, then the Laplace transform of it is just the expectation of some exponential random variable related to x. Okay, so that's that observation is very important, and I'm gonna probably dedicate another video to discuss the applications you can get from this realization. In other words, if you realize the Laplace transform as the expected value of some interesting random variable, you can get some cool stuff. Let's keep it this vague. And of course, just as we discussed before, just as we know from a theorem that we've proven above that the derivative of this, first of all, we know that this thing is differentiable. It's complex differentiable function, and we know that the derivative is obtained by passing the limit as h goes to 0 to inside, like to the inside. But this is the same thing as interchanging derivatives and integrals. In other words, for Laplace transform under the assumptions that we presented, it's the way you differentiate a Laplace transform is by interchanging the derivative and the integral. So this is justified for Laplace transform. And if you differentiate the integrand here, you will see that the derivative of the Laplace transform is the expected value of the original random variable you started with. So I'm gonna leave you with that, and I'll let you think about it, let you think what kind of application we can get from here. But it's interesting to observe that the derivatives of Laplace transform of some density functions are just the moments of the random variables, the corresponding random variables. Okay, so I'm gonna leave things here, and we're gonna probably discuss more properties and more applications in later videos. But for now, I hope that I gave you a little glimpse of what this is about, and then we're gonna follow this by a later video. Thanks for watching.